Okay. So, if we follow from the previous week material, we are discussing the issues of how we can design antennas if they are put in a specific array, with this regard, what it is very important for us. Good morning, everyone. What it is very important for us is trying to determine, given a specific. Sorry, let me just figure out what part of the board you are still looking. I thought the camera was fixed. So the elements we're discussing currently in chapter 7, first of all, we're discussing possible approaches of how we do this modeling. And from the previous times, we said that we have few techniques such as Shekulnov polynomial method and the Fourier transform method, including also Woodward-Lawson. What we are going to focus the most, it will be Shekulnov and the Fourier transform method, and especially the second one. It is an interesting approach. Not approach, it's something which is which we can also call this intuitive approach, because whenever we try to determine some important parameters, we're going to observe the existence. So let me write here. So the two techniques we're dealing so far is Shekulnov. The spelling I'm not very good, or the Fourier transform. Now, with the spelling, I'm not very good at this stage because it's hard to memorize all different spellings of even the Chebyshev polynomial. It's strange, but if the Russians spell it one way, we notice that in the textbook of Balanis, they even spell it in a different way, which the last names of people, they should not change very often. And this Shekulnov, if I try hard, it was maybe. So this was the first method, and this was Shekulnov polynomial method. And before we solve a few examples, I would like to go over very few slides as a reminder, so that when we move to the okay. So this is what we are trying to. These are the models that we are discussing, and the essential aspects that we really care a lot is the definition of the array factor, which is shown in here, and then in fact in this array factor we have n different antenna elements. So let's see that here we can have the first one, the second, the third, and we go on like this. And then in this array factor, we're going to add all of these numbers, and let's notice for a moment that we have actually two important aspects. One is that whenever we're trying to design the antenna, especially in the Shekulnov method, we try to determine what are the nulls of the radiation pattern. When we talk about the nulls, we're trying to define the regions where the intensity is going to be equal to 0. So we may assume think about this one in this way. First, we want to have a visualization of how the radiation depends on angle theta. Thetas, we measure these. Actually, I'm sharing the slides. Students cannot see very well, probably. But initially, we're talking about this kind of theta. And then we have another important visualization of the whole problem, where we have the plot of psi. Yeah, psi. Lucruri sunt dale și în colegioi. Cam pasă, deci Povestim educata, e dilom felice pa smije profesor. Are gerazi, që s'po këshirisht shumë me kujdes një dhe pas smije profesor. Ke folë qitë leksione, ke qytë psajt, në kërë psaj, shajeta, për një marit. është mirë kur kështë të dëshme që nuk të staton shumë drejtën sytë. We're not native speakers, but So whenever we have this design of the antennas, we know that we start from the first one, so this is the array, and we go up to n, and then we give the constraints of how the nulls should be. So we have to figure out what this dependency on theta will be, and then we have also some other important parameter, which is this the letter psi, and psi is in fact, we can think about this one. Psi is a function of distance d and beta, okay, where d is the distance between any two components, okay, so this is the distance d, and then we have also the complete length of the antenna, which often, this is given something like this, L is equal to n lambda. We have also the distance d, which is often given, I don't know how to call this one, but let's call this one, so n is traditionally, let's consider this one larger than lambda, but we are doing this one because we are assuming we have few components, okay? Because the distance can be sometimes half of the wavelength or one wavelength. Let's assume here we have n is just a number and it's not equal to this n. So we can also call this one L is equal to md, maybe this is better to write it this way, m, let's do this one, m lambda, and in this case m, it is smaller than lambda for sure, but we want it also to preserve some important properties, so let's even consider this one smaller than 1/2 in the most general sense. So then this L is equal to md, but we can write this one also, n, the number of components, times the d, which is m times lambda. So these are the important essential parameters at this stage. And whenever we put some constraint on the radiation pattern, we should really follow carefully which one of these parameters we are having the constraint onto. So initially we give the psi, we can see it from the slide, equation 7.7a. This really shows how the psi depends on these two factors, d and beta. And let's move ahead here. And then we notice that also the exponential term which appears in the AF. Okay, so let's have a look for a moment. Well, let's write it here. The AF is equal to the summation of all the antenna array components. So this is going from 1 to n, and here we have the an multiplied by e to the power n minus 1 psi. Exponential, so this is the exponential j n minus 1 psi. Now I should have it in a slide, and so psi is equal to kd. So psi here we have it in here. We just do a change of variables, which will become useful when we do the analysis using the Shekwerov polynomial, where from all of these equations we can observe, yes, I think, let me think for a moment, this is z. This is all this term, psi, we can, this is going to be the z to the power n minus 1. Okay, so this is how we can, I believe it might be better, sorry, I should have seen it by now. Okay, I thought I had it somewhere. No. Apologies for going all this way. But, okay. So when we do this analysis, we're going to, especially the polynomial analysis, we're going to express this as a function of z. And this is polynomial of degree n. Let me see. Just want to refer you to the exact expression in the textbook. Yeah, e to the power j psi, e to the power j psi. So these z's actually are going to appear in the polynomial. So in fact, if you're given any polynomial of degree 3, that immediately means that we have an antenna array which has 4 components, okay? Because polynomial of degree 3, n is equal to 4. Okay, and let's see here. Now, here we have the z-plane. Now, what the z-plane stands for, this is in fact we define the visible region, which is the region where we can obtain the zeros. Let me say it. Let me think for a moment. This is how we can define these. And for example, let's see here, for this specific domain, we get wait a second. So if you have d equal to lambda over 8, we can multiply 2 pi divided by lambda. So the third line in this slide so this is kd. So this kd, it's here kd, then we get pi over 4 cosine theta. If this is pi over 4 cosine theta, this means that the psi, since cosine can have values from -1 to +1, then we can say that the psi is anything between pi over 4 and minus pi over 4, so which is from minus 45 degrees to plus 45 degrees. So this is let's call it, in the space of psi, or in the domain where we understand the value of psi, this is what we can define here. But let me think also regarding an important aspect. So overall, what we are going, so let's have a look at this equation 7.7a. If we want to design a system of antenna, of which we don't know the number of the antenna components yet, but we know, for example, that we want a null around, let's say we want a null at theta equal to 90 degrees. So the real space where we do the measurements is this one, and we care about some angle theta, which can be described like this, and we want a null at an angle of 90. Then what this means for the constraint put onto the psi is that we have here pi over 4 times cosine 90. Cosine 90 is equal to 0. So that means that the psi has to be equal to 0. And which means that this is going to correspond to this value of psi. But if we want a null in the real space where we are going to do the measurement at an angle of 30, then we obtain a value for the psi, which will be equal to pi over 4 times cosine 30, which is going to be something like pi over 4 times square root of 3 over 2. So this is going to be square root of 3 over 8 times pi. This will be the, so let's even write a couple of values here. Let's check out. Apologies, so this does not right. I cannot make 0. Okay, so if this is going to be equal to 30, sorry for not being able to write this one correctly. But what I want to say, I can write this one also on the board. I want to say that we have a constraint on theta, and this constraint on theta provides a value which corresponds to a psi, and this exponential times j times psi will give the z. And this z, we're going to see this one into the polynomials in the order n-1 z, which means that this polynomial is going to include terms which are z to the power 0, z to the power 1, and up to z to the power n-1. So we will get used to looking at polynomials of this form. Now, let's. In fact, before we go to the, I'm just wondering. Let's do an example. Let's let's try to figure out how can we design an antenna which can have a null at angles of 0, 60, and 120. So let's assume we want a null here. So we don't want to measure anything at that domain. 60, 120, and 180. 60 is here. This is another 60. And so apparently we want to measure 0 here, 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 and here. And let's also assume for a moment, so these are the nulls. Or when you write these, let's do it like this. This is equal to 0, 60, 120, and 180. And before we go to the future topics, so let's assume we want yeah, these were the nulls. Then if these are the nulls, then we should, let's also assume that the beta is equal to 0, and after the beta being equal to 0, let's use also a d equal to lambda over 4. D is equal to lambda over 4, which is the distance between any two subsequent antenna components. Actually, I thought I had this. Să tu cam slide partly two or section where this is. I need to touch about. I'm missing something. Okay, so we have these thetas, and the first thing that we should start considering is the following. What does the psi look like? This would be equal to kd cosine theta plus beta, and this will be equal to kd, k, this is 2 pi over lambda, d is equal to, we said lambda over 2, it should be lambda over 4, let me check again, this is lambda over 4, so this is the kd, cosine theta, beta is 0, so we do here plus 0, which is almost clear. Now we get here pi over 2 times cosine theta. Now pi over 2 cosine theta, this is pi over 2 cosine theta, then we should get 4 different values. When theta is equal to 0, so let's consider this the first one, the first component. When theta is equal to 0, cosine theta is 1, this is psi is equal to 1, that's the first value. Then, when we set theta at 60, what is cosine 60? Cosine 60 is square root of 3 over 2, and the psi will be square root of 3 over 4, this is times pi, right? Or let me think. Yeah, even this is right. This is pi over 2. That's correct. This is pi over 2. Then we have 3 over 4, square root of 3 over 4 pi. Then we're going to have, so for each theta, we're going to observe, we're going to get the different psi. But now, before we do this, and to prepare us for the next value, if we have psi equal to pi over 2, so if psi is equal to pi over 2, we're talking about this angle, okay? And at this angle, e to the power, so let's try to evaluate this now. What is the value on the unit circle? What? So cosine 60 is 1 over 2, that is true. So we get here pi over 4. That is true. Okay, so that's correct. This is pi over 4. But for a moment, it might be good to think about, you know, the unit circle, right? unit circle where we draw the e to the power I theta. Well, let's put it j. So when psi is equal to pi over 2, să de n și here either do that. Oh, Cristina, again. Also the other one. Let's have a look at this one. So this is the complex plane. The horizontal axis is the real part. The vertical axis. Yes. So what can you say for z? Or what is z when psi is equal to pi over 2? Because
pi over 2 e o 0 nici.
0 nici. What are charge 0 nici?
Asta 0 cosinus e veni.
Oh, but that is up to direct. Let's read this here.
Yes.
What is this? Pra, kur rrotullojmë kënd i të dytat, po rrotullojmë me lodhin gjatë. Ku shkon kjo? Kur është këndi 0, sa është n fuqi j theta? Kur është këndi 0? Është nish. Pra, kjo këtu, ne gjejmë vlerën nish, ku këndi është 0. Po kur është pi të dytat? Po patjetër, po. Se po mendoj, është complex plane, po duhet të shoh. Pra, ku këndi është pi të dytat, sa del vlerë? Po mi 0 nish, po çfarë vlerë ka? Është here. Është here. So here, this is the j, which means that if we have pi equal to pi over 2, that means that in a complex plane, we are rotated by an angle of 90 degrees. So z1 is equal to j. Okay, so this is what we care for the moment. Z1 is j. Then, when psi is equal to pi over 4, as Bjorn corrected us, what is this? We are rotated by an angle of 45 degrees. This is pi over 4. So this is Z1. Now, what is Z1 here? Z1 here, we can write this one. The magnitude is 1. So this should be, what is cosine of 45? It's square root of 2, or let's do it 1 over square root of 2. 1 over square root of 2 plus j times 1 over square root of 2. So this is Z1, right? So this is the second value. Then let's try to find, so that's why it's good to go back and forth. Now let's do the next step. We did theta 0, we did theta 60, and we got psi is equal to pi over 4. When theta is 120, what is cosine 120?
It's minus 5, minus 102.
Po cosinusi, but the cosine 120, that is correct. It is cosine 30, right?
Minus cosine 60.
Minus cosine 30. Okay, minus cosine. I have to impose that on. So this is 120, so we're looking at this one. So cosine, it's minus cosine 30, yes. So here we're going to get minus pi over 4, is it right? Yeah, I think that is correct, because this is the angle 30, when theta is 120. We're looking for the cosine, and this is really 1 over 2, but with negative sign. So psi, it will be equal to minus pi over 4. So minus pi over 4, that means that, so let's not forget, we're trying to draw here the angle psi in this domain, and then that means that Z1 was j, sorry, this will be Z2 now, right? Z3, it will be the e to the power j times minus pi over 4. So here, this will be equal to 1 over square root of 2 minus j times 1 over square root of 2. Are we clear here? Okay. Now, the next step, the final step, is that for theta equal to 180, then, so we are just actually, we have the fourth value. We have to evaluate this psi for four different values, right? So when angle is 180, cosine 180 is equal to what? It's minus 1. Minus 1 times pi over 2, so then this psi, it will be equal to minus pi over 2. So this is minus pi over 2, so we can see this on the board. When psi is equal to minus pi over 2, So if one by one, we had pi over 2, then we got this pi over 4 minus pi over 4, now we get here. So when psi is equal to minus pi over 2, that means that we rotate it this way. What is that for?
It's minus j.
That is correct. This is what we care. This is minus j. So actually, we wrote them over there, but let's have this z1 is equal to plus j. So here we have 4 roots of the polynomial in z. So let's not forget, we were defining the polynomials in z. So, and then we know that if we have a polynomial of second order, where the first root is equal to 2, and the second root is equal to 3, what does the polynomial of second order in x, what is this going to be equal to? This will be x minus 2 times x minus 3, right? So this is the polynomial that has these 2 roots. So at this stage, actually, what we need to do is that we need to determine this polynomial, but to do this, I may have to raise some small components. And let's take this out. These are some equations. Let's also take out this part. And now our polynomial will look like polynomial in n minus 1, which is actually AF. So this is the array factor. This is what the polynomial that we can evaluate and figure out the power distribution. So at this stage, this will be equal to z minus j times, because the polynomial should be in z, that's the variable, minus, then we have z minus these values, minus 1 over square root of 2, minus j 1 over square root of 2, times z minus 1 over square root of 2, plus j 1 over square root of 2, and multiply z plus j. Okay, so this is the polynomial. The highest power, it is z. So the polynomial, it has 4 roots. It has Pn is 4. So what is the number of antenna elements that we should obtain? Now, this is polynomial in n minus 1. Ce o polynomial gratis care che mi pes. So this polynomial, this is in fact p, n minus 1 is p4. So if we equal these two together, that means that n minus 1 is 4. So for this design, if we want to have these zeros at those 4 different angles, we want to have an antenna which has 5 different arrays. So far we've done this one. We have too much. We have some more information that we want to figure out. And what is this new, the other type of information? The other, actually, let's do it here. 1, 2, 3, 4, 5. Actually, we have 5 here. The next important information is this. What is the excitation coefficient? What is AN? So this is what we should figure out. And where do we get this AN? These ANs, we get these values from the coefficients of the polynomial. So we are going to expect that this one, A1 times z to the power 0 plus A2 times z to the power 1 plus A3 z squared plus A4 z to the power 3 plus A5 z to the power 4. So these excitation coefficients are hidden in this polynomial. So when these are the roots, we have to express this whole expression into a similar form. So we have to separate the constant terms, because z to the power 0 is 1. We have to separate z to the power 1 quadratic cubic terms and the terms z to the power 4. Now, if we do, let's see if there is some way to do this easy. So z minus j times z plus j, the multiplication of these two factors. This is equal to, let me think for a moment, this is z squared minus j z squared, so this is equal to z squared plus 1. So the multiplication of this and this is z squared plus 1. This is z squared plus 1. And then here we have z minus, can we express this one?
Të minus një ndaj rënje dyshit, minus të pjesën, dhe pastaj ke shumëzën të pjesën, që I bje z minus një ndaj rënje dyshit e gjitha në 4, minus...
Eksakt, shumë ke shumë të drejtë. Pra më të bëjmë në këtë formë, më themi që kjo është z minus një përmbi rënjën e dyshit, kjo e gjitha në 4, minus atë tjetër në 4. Një përve që ke i në 4, minus që bëhet plus. Pa këtë bëhet plus, në 4, një gjitha. So, then, it should be this one. This is, let's expand this one first. So this is going to be z squared, wait a second, yeah, z squared minus 2ab, minus 2z over 2 plus 1 over 2, right? Plus 1 over 2 here, plus 1 over 2 is plus 1. Plus 1 times z squared plus 1. So this is how the multiplication will come out. And then this will be equal to, let's z squared times z squared, we get z to the power 4, but this is 1 times z to the power 4 plus, so we get the z to the power 4 by multiplying this term and this term. Let's get z to the power 3 term, so this is going to be minus 2, actually let's do it, z to the power 3, then plus 1 times z squared plus, we should have, no, we have another z squared. Wait. Kemi dhe këtë z katrorin këtu në të dyja. Atë dhe dysh edhe. Në fakt, njështi mund të ka hi diçka në speseve, për z katrorin marrim.
Z kushit ka minus rënja dyshit z kushit 5, plus 2 z katror, minus rënja dyshit z, plus 1.
Minus rënja dyshit z, kushit 1. Minus rënja dyshit z për 2, plus 1. Okay.
është thjesht minus rënja dyshit z, ka atë dyshit, me që është bërë për
Për ka dyshin kjo. Se ku shënëtohet gjithë faktorin në njëshin, edhe të dyrë të mjëra e dyshit z.
Dhe dy, besim për një dyshit, dhe një dyshit besim.
Dhe një dyshit për një vjerë një dyshit të të më përja.
Më të thash, dhe një dyshit.
Të 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 të. Po, këtë drejtë. Qëtë të në të rëjë dyshit, rëjë dyshit z. Plus 1. Okay, so from here, what you observe is that all of these coefficients, which the excitation coefficients that we're going to have here, they will be, so we have to equal A1, it's equal to this A1, so this is the 0th order, and then A2 is going to be minus square root of 2, so it's going to be minus 1.4, and so on. So this is how we are going to relate these two together. A3 is equal to 2. let's write them here. So A1, this will have an excitation factor of 1. Then the next component is minus 1.4. Minus 1.4. The third component, it is 2. So actually, it's reading these backwards. So here, the excitation coefficient is 2. Then the next one actually is just square root of 2. Minus square root of 2, so it's minus 1.4. Minus 1.4. And then we get 1. Okay. So for this antenna, it looks like even the excitation coefficients, they are to some degree symmetric, right? So we get here the center antenna element, it will have an excitation amplitude twice with respect to the ones in the edges, and here we get minus 1.4. But actually, when we have this minus 1.4, we can also think about this one in this way. The excitation factors or the waves that we have to, let's erase this one. This was just to figure out what were the z as a function of the angle psi. We can also think about this one this way. The harmonic wave which will be fed into this antenna, it can look something like this. Amplitude is 1, and we can consider the cosine or sine. Let's put a sine, okay, it's not a problem. So we give a sign after pi over 2, it will be maximum, it's going to be 0, again here, and here. So this will be the excitation initially, and amplitude, we put it 1. The next component, it will be minus 1.4, but minus 1.4, we can also think about this one as if the amplitude, it will be 1.4, but the phase difference is 180 degrees. Okay. So it has a phase shift of 180. So if we are to draw this one here, it will be the same way like this. Amplitude you multiply by 1.4, but it will start right here. So we're going to do alternatively. So it will be delayed by this much, so it will be something like this. Here, here, and here. So this will be the respective waves which will be applied. This component, it will have something which is in phase to this one, but amplitude is twice as more higher amplitude. This one, it will be similar to this, and this one will be similar to this. So this minus 1.4, this can be, you can write it also this way. This is 1.4, but the phase angle, you can consider this one, theta is 180 degrees. So it's the same way of representing.
How do they combine constructively in this case? The equation to split and
well, they don't combine constructively. I mean, because of destructive interference, we get these nulls, which are, so we have nulls here, 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 here. And of course, they will interfere constructively and destructively. So in some directions, they're going to add up together, but in some other directions, we're going to get zeros. So if we are to draw this antenna, not draw, but the power, radiation power, it will be, so here we have an angle of 60, this is 120, and then the distributed power is going to look like this. Because we have a null here, 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 and here. Okay. So they do interfere destructively in this direction, and so if we put another antenna to pick up a signal from this radiating pattern, and the first thing I think about an antenna is loop antennas. I like them a lot because they were very helpful when we had a very bad TV stations experience. So they used to pick up signals from very far away countries using the loop antennas. That's why we like them a lot. So think of putting a loop antenna right here. I measure nothing. I can put another loop antenna right here. I measure nothing, of course here, and another antenna here, and another loop antenna here. Now, if you're not very too much patriotic about loop antennas, we can also put line antennas, which you can buy with a cheap price on the stores, or at least these are more common. Do you have any question for what we did so far? At the beginning of this session, I just wanted to go over the slides to kind of remind these equations that we explained the theory in the previous week. Okay, if there is no more question.